Hi, back again with the procedure and how we're going to conduct our sample calculations. So again, what the lab is looking at is the formula of a hydrated salt. And how we're going to do that is heat it up and remove water. And the differences in the masses from the original sample that we weigh to the sample that's been heated will tell us how much water has been removed. So one question you might ask, what's the purpose for hydrated salts? Well, hydrated salts are used in desiccators. Here's a desiccator with a salt, a hydrated salt that's blue. Now, what we get is the use of these act as an indicator to us by our eyes. If we see a color change, we'll know whether the sample is fully hydrated or if it's in its anhydrous form. In that case, it doesn't have water. The purpose for using these in a desiccator, such as I just showed you, is to dry samples out. Once we have recognized that a color change has occurred in our salts, then we know to remove it, replace it, and put fresh sample in there to make sure that samples that we're putting in there that we're using in the laboratory stay dry. So that's one of the reasons why we use hydrated salts. I believe Palermo's virtual lab discusses how these are used in little packets and a lot of packaging that we do when we're mailing things. You probably have seen them. Do not eat these silica gel samples. They absorb water. So today we're going to take a sample that's a copper sulfate and it's a hydrate. And what we want to do is figure out what X is. X is going to be a number, a whole number between 1 and 5. And that'll tell us what the formula for that hydrate is. This can either be copper sulfate. If that's a 1, that's monohydrate. If it's 2, if we experimentally determine that's a 2, it's dihydrate. If it's 3, it's trihydrate. 4 is tetra. 5 is penta. We'll be determining this experimentally. So what we're doing is we're taking our sample, the copper sulfate that's hydrated, we're going to heat it, and we're going to drive off the water, and we're going to end up with copper sulfate and a certain number, X, moles of water that we're going to experimentally determine. So let's go over a little more detail of the experiment. Let's move over here. Stop, settle down, okay? So, if you were working in the lab, you would get a sample, unknown sample, it's blue, and for copper sulfate, when it's blue, it's carrying water with it. And what we would do is take a small scoopula, our sample, and we would scoop it out into a ceramic device known as a crucible. Put the cap on. We would handle this carefully and weigh it on a balance, such as we did in our last experiment dealing with density a few weeks ago. So for instance, if we took a sample, put it into our crucible, and weighed it, and we got a mass of 0.1873 grams. That's right here. That's our original mass. What we would do is we would set up a Bunsen burner. I don't have the gas hookup in this lab, so I'm not going to actually go through the apparatus. Palermo's experiment, the virtual experiment, does show the Bunsen burner, the ring stand, and we would have a crucible. Now, this is an open crucible that you can see the sample. It's blue when you put it on the flame, and you would heat it. Oftentimes, this takes anywhere from 5 minutes to about 15 minutes. And what you would recognize is that the sample goes from blue to white, and that would indicate to us that we removed all the water in the sample. We would let the crucible cool, and we would re-weigh the sample. If I re-weighed the sample, and I measured its mass as a 0.1193 grams, The difference between the original mass and the final mass, well, that's due to the water that we've driven off. And that's important for our experimental calculations. So the mass of water that we've driven off is simply the difference from our initial mass subtracted from our final mass. And this is the mass of water, 0.68 grams, that we've removed in this experiment. Important other pieces of data that you're going to be using. Now that we know the mass of water, we're going to conduct a few other calculations. So let's get this board set up. One thing we're asked on today's procedure is what's the mass percent of water in the hydrated salt? And that's asked on today's experiment. So mass percent. So when we calculate a mass percent of a particular substance that we're experimentally determining, in this case, the mass percent is the mass of water that we've calculated that we removed divided by the initial mass of the hydrated salt. And we would multiply that ratio by 100%. So let's put our numbers in there from our data that we've collected a few minutes ago. So if you look at the data, you might want to have this, you can look at the video again. This is simply going to be the mass of the water divided by the initial mass of the hydrated salt. The original mass is 0.1873 grams. And we would take this ratio and multiply it by 100%. And that would tell us the mass percent of water in this hydrated salt. I got 36.3% water in that sample. Any questions so far? Everybody got that? Write this down in your notebook. Keep track of this. We're going to also find out what the formula of this sample is. So let's remember what's happening so we can understand why this is true. We're taking our salt that has an X amount of water in it, and we're heating it, and we're going to end up with some copper sulfate plus X amount of water. Now, this is a reaction that we can use some information about that we're going to explore in Lab 5. But when we look at our reactants and our products, we can imagine that there's coefficients in front of them. This tells us that we have 1 mole amount of this sample, and we end up with 1 mole of copper sulfate. What we're trying to figure out is how many moles of water X that we removed from the sample. So the first thing we need to do is we need to find out how many moles of water. How many moles of water? We're going to use the molar mass of H2O to figure this out, and the mass of water. So if you recall from our discussion, this is the amount of water that we've driven off 0.0680 grams of water that were removed. And what we want to do is we want to figure out how many moles of water that's associated with. So we're going to need the molar mass of water. Remember how to calculate the molar mass? We have 2 hydrogen, we have 1 oxygen, and we need to account for the masses of each of these. And we sum them up. And we would find that the molar mass of water is 18.02 grams per mole. Well, what we're going to use is if we're given the mass of water, we're going to divide by the molar mass, and that's going to tell us the number of moles of water. Really, it's an exercise in dimensional analysis. So we're given a unit of grams. We're going to put 18.02 grams in the denominator. Grams cancel out. And if we take the mass of water divided by the molar mass, that's going to tell us how many moles of water were in that sample. In this case, I got 0.0037736. Okay. Well, to determine the formula, we need also to figure out how many moles of copper sulfate are in this compound. So to determine that, let's ask that question. How many moles of copper sulfate? Well, what we need is the mass of copper sulfate, which is the final mass from our experiment, and that is 0.1193 grams. That's the final mass. And the final mass is the mass after we've removed all the water. So that's just the mass of copper sulfate. And just like we did before, we're going to divide by the molar mass of copper sulfate. The molar mass of copper sulfate is 159.62 grams. You would account for the single copper, the single sulfur, and the 4 oxygen, and sum up their masses from the periodic table, and that would be 159.62. And that would give us the number of moles of copper sulfate. 0.0007474. That's the moles of copper sulfate. Everybody good? Everybody got those numbers? So there's the moles of water that we've calculated. There's the moles of copper sulfate that we've just calculated. We need to figure out X. X is the number of moles of water. We need to determine that by taking the ratio of the number of moles of water that we removed over the number of moles of copper sulfate that are present. And that's what this value of X is. X is the number of moles of water over the moles of copper sulfate. And we're going to round it to the closest whole number. Hopefully Palermo set it up so that they're usually going to be pretty nice and rounded to a pretty close number. So let's set this up. There's the moles of water, which is the largest number. So whatever ratio you use, always use the largest number in this case. divided by the number of moles of copper sulfate This is going to be 5.05, which is pretty close to 5. So what our experiment has showed or helped us to determine is that the formula for our substance in this experiment, copper sulfate pentahydrate. And since this is a transition metal, this is copper 2 sulfate. Pentahydrate. Penta indicates 5 moles of water for each mole of copper sulfate. So good luck on your experiment, and I'll put out experiment 5 as soon as I can. Good luck. If you have any questions, send me an email, and I'll put together more discussion on YouTube, or I'll just answer it for you. Have a nice day. Be safe.